Okay, so in this video clip, I'm going to take a look at Google Colab charts. So we go to Google Colab, and I'm in the Chrome browser here, so that's generally recommended. And then I come across here to the Examples tab and come down to Charts in Colaboratory. That sets out a number of visualization tools or libraries available in Python. And the one that's most commonly used is probably Matplotlib, but other popular tools include Seaborn, Altair, Plotly, and Bokeh, and they're all set out here. What I've done in terms of developing this material, I'll leave a link below the video to the original charts, but I've also created an additional or amended this Jupyter notebook and put in a few additional comments, and I'll leave the link to this charts and Colaboratory as well. Okay, so I'm going to go into the amended one with a little bit more text in the text cells, outlining a little bit more the history of the different libraries and so on, and a little bit maybe some intuition and logic. So as identified, the most popular visualization tool in Python is probably Matplotlib. The genesis of this, if we go back 20 years or so, MATLAB was probably one of the more popular tools used by engineers and people in the quants community, and it had a graphing package that was very powerful, but there was a paywall on this software, and people in the Python community wanted to develop an analog or an equivalent type capability in Python. And some of this clustered around the efforts of John Hunter in 2003. And they built basically a website with tutorials, with examples. They provided in an open source, so no paywall here, the open source code on GitHub, and also a fairly substantial community, because of the critical mass, a fairly substantial community of people who had encountered problems posted fixes. So that became also another very powerful accelerant here in terms of generating a lot of popularity in Matplotlib. More conventionally, since the arrival of ChatGPT, typically if people have error in their code or for graph misfires, you can go into ChatGPT, post in the error, and it'll resolve also some of the problems that emerge incidentally. So, okay, if I go to the first code cell here, and we run the code that we have, we generate a line plot. Line plot here, we have two lines that we're generating, all based on the same x-axis of values going from 1, 2, 3 up to 9. And then we've different values here. So I've done the same here in this Colab. And, we could play around with that a little bit, but say, for instance, we wanted to change this to maybe 4. To 4. And just observe the effect there. You can see how we have dynamic control over the graph. So on the x-axis here, we've 1, 2, 3, 4, 5, 6, 7, 8, 9. That's what's on the x. And then we populate the y values, 1, 2, 3. Maybe we could change this to 6 so that the two lines actually kiss, y1 and y2 kiss. And we can observe the effect down here. And then on the x-axis, we could say x1 axis, if we just wanted to demonstrate a little bit the effect of changing our labels here, we have x1. And on the y-axis, then we have the y, so we have both y1 and y2. And the line graph example let's say, I don't know, big example. We run that code, you can see we can actually control the title of the graph as well. Okay, now a more complete set of some explanation here is provided in the text cell above, so you might take a look at that as well. Okay, the next graph that we look at using Matplotlib is bar plots. And you can see here with the bar plots, we're generating, we have two series of values. So we have x1 and x2. They range from 1 to 10. And then we have our y2 values 5, 6, 2, 6, 2. Okay, so for the most part, 1 and 4, if we look at 1 and 4 here, so we have this, the value in the x1 is 1, and then 4. If we change this value here to 5, or to, let's change it to 10, we'll change the nature of our graph, will go up to 10. So now no longer 1 to 5 or 1 to 10. And that's on the blue. And then x2 and y2, they both basically coalesce, and it's all turned to value. But we can see here 6 is shared by x1 and x2, 6, and here we have 6. So 1, 2, 3, 4, 5, and that's 7. So 6, 7. 6, and the blue is 7. And underneath we have 6 and 2. 6 and 2. So that's the green part of that bar chart. So they overlap where the values, where the x values are shared. And you can see we have the same type control. Now we could change maybe the color to red. Right, so we could go in and change some of the coloring here. I think blue is probably preferable. Okay, go back to blue. It's easier on the eye. Blue and green go together sometimes. And or we could go, let's see if we can change the black. And I'll put BL. See, does it recognize that? It doesn't, but it might recognize ACK. Okay, and we're getting black here. Okay, now if you had a problem with the code, if an error came up, you could go to Stack Overflow, or if you had the error printed up, just copy the error and put into ChatGPT, and it'll come back with a solution. Okay, histogram. If we're running a histogram generally provides us with a sense of the distribution of values. Now here, we're generating a series of 1,000 values randomly. So we're synthetically creating 1,000 random values. They are going to have a normal distribution. So they'll have a mean of 0 and a standard deviation of 1. And they will be centered around 5. So when we map out, we're going to get 3 plots. One that provide us with a histogram, the first one. Then the second graph will be, so the first graph is the raw data. The second graph is the histogram. And the third graph is a cumulative histogram where we've defined the bins. Okay. Now, if we run the code, that's the output that we get. It might be useful to take a look at that n for a moment. If I just go in and say, okay, well, what does n, let's go back, pause here for a second. Okay, so we're taking a closer look at n here. And n was generated by randomly producing 1,000 values that have a mean of 0 and a standard deviation of 1. When we run that code, of course, it produces the 3 graphs. So the raw data, the histogram, and then a cumulative histogram, right? And of course, we have a series of 3 plots altogether. To understand a little bit n here, if we just go in n, because I've written n, right? And if we want to take an overview what n represents, it's basically we have 1,000 values of n here. And that's what these values that are randomly generated are values that go in to populate the first graph in the series of 3 here. So that's what our raw data is based on. And you can sort of see here that we have a mean of 5, and then we have values distributed around the 5. And perhaps to get a sense of how that actually works, we could take a look at perhaps the descriptive statistics for n. So if I go back in and convert n into a panda series. Now this probably won't work because I don't have pandas imported. Okay, so we haven't, to access pandas, which is the data transformation package that Matplotlib very often relies upon in order to take the data transformation. So if we import the pandas as PD and run that code again, we can convert n that we just looked at into a panda series. And then to get the descriptive statistics, we can take the print the statistics. Now, maybe a nicer way of doing that would be just put, say, stats, right? So we have a mean of 4.94. If we change our series maybe to 10,000 here and run again, we would get closer to 5. So it takes a little bit longer to generate. So if we generate 10,000 values of different n, should have a mean of 5, and the mean of the random number is 0, and would have a standard deviation of 1. So when we graph here, we should get raw data that's much more densely packed, and then maybe a nicer shape on the histogram, and likewise here as well for the cumulative histogram also. Then when I run this again, I will get 10,000 of a count and a value close to 5. Okay, so we're getting now 5.002, standard deviation of 1, and then these percentiles would conform to the normal distribution. Okay, so that's what, if we changed our values, if we generated, let's say, 10 values here, and we mapped out our raw data in the histogram, you can see here the raw data is, okay, would have a mean of 5 roughly. The histogram, because there's too few values in the sample, it's very skewed, doesn't have any type of tapering. And then the cumulative histogram also doesn't really look like a normal distribution. If we take the mean, if we take the descriptive statistics there, you can see we're quite a bit away from the mean of 5, and the standard deviation is not quite 1. So to increase the accuracy, probably go up to 10,000 and run that again. It's a little bit slower because there's more values now to compute, but it will generate a more smoother type histogram. The histogram would conform maybe more to a normal distribution, or our conceptualization of what a normal distribution would look like, where the mean in this instance is 5, standard deviation roughly 1. And we can see that here when we do this descriptive statistics. So mean of 5, standard deviation virtually of 1, and then the percentiles aligned to the normal distribution. If we change the bin size here to 10, and the bin size again in the cumulative distribution to 10, we'll see a smoothing out of the distribution as well, right? Given that our sample size is relatively big, but it does take a little bit longer for the visualization to render because now it's got to perform much more work. Okay. Okay, so it's a little bit perhaps lopsided. Okay, if we raise this to 100,000 values, I'll run and pause the video clip. Okay, and you can see that took a little bit of time, 2 minutes to execute. But we do get a slightly more, there's a bit of skew here, but a slightly better rendering of a normal distribution. So it probably makes sense if we revert back to the bins of 20, that looks as if it would be optimal. And run that again, right? So if you generate a lot more random values, it takes a lot longer. The 1000 looks quite optimal. Let's just run that and I'll pause again. And this time that ran in 2 seconds. We can see here the 2 seconds and the tick. And what we get is the 3 graphs that are being, so this is our raw data that's generated synthetically using simulation. And then we plot the raw data, which is just basically n. And then, so the n is the values, and we have for the range, so we have, that's our raw data. So 1, 2, 3, 4, 5, the first value, the second value, the third value, the fourth value. That's been outputted all the way up to 1000. That's how we generate the raw data. And then the n then is a classic histogram is provided, which puts each of the raw data, all the raw data gets put into bins of 20. And then the cumulative distribution, right, which we hear, if we say false, it reverts back. So false, SC, false. Let's try lowercase. Let's run that. And it'll just give the second histogram then is no longer a cumulative histogram. It just becomes the same as our regular histogram. So we'll put that back as true. Otherwise, we could leave as is. So let's put in true. TRUE. And we go back to the cumulative histogram. Okay. Okay, so scatter plots then. Scatter plots are generally, I've left the interpretation here, but the scatter plots here we have x1 and y1, so as a series of values, so 2, 5, 3, 5, and 4, 5, those points will be mapped out on the plane. And then we have a series of the second index is a twin set of values. So we'll have 5 x's and 5 corresponding y's for y2 and y3. So in the scatter plot here, the first x1, y1. So x is 2, x is 3, x is 4, and y in each instance is 5. So that's the values we have here. We could change this to 5.5 and run again. And you can see the middle one has just gone up to 5.5. If I go back to 5, then all of those blue dots, and that's the default rendering, level out. Okay, to understand then x2, y2, y3, well, the y2 values are lower than the y3s. And for the x2, y2 values, we're going to put in a v. And for the x2, y3 values, we're going to put in the circumflex, which turns out to be a triangle. So the v is the inverted triangle. And the circumflex, want of a better term, becomes the triangle. And that's for the higher range. Okay. Stack plots then, again in Matplotlib, I'll leave the interpretation available here so that you can go back and read. But our rendering here is going to map out one graph stacked on top of the other. And D1, D2, D3 corresponds to the ARR1, ARR2, ARR3. So the index is 1 to 9. We can observe that here. And then we have a series, the first one, 123. 123. So we could say, let's put this to 10 or to 5. And let's just observe the effect when we do that down below. You can see we've pushed this down to 5. And the other values fall as well. So 5 up to a little bit over 20. So that's that. So 5 and 17 is 22. And that's why we're getting 22 here. And then a little bit less than 40. Because 15 and 22 is 37. So that's roughly where we're getting 37 here. So you can see we stack the diagrams. That's a very powerful way of presenting graphs. It's obviously, if we have a series of data points and we want to make the direct comparison between the magnitudes of 2, 3 series, stacked graph is a nice way of doing that. Also, it's probably worth noting the command we're invoking here is stack plot. On the x-axis, we have the values going from 1 to 9. Then we have ARR1, ARR2, ARR3, and our different colors. If we wanted, instead of the blue, black, we get a black, or we can change back to blue. And if we wanted help with that, maybe a better, just the nomenclature for the different colors, we could go to the Matplotlib library or try ChatGPT. Right, now pie charts are also a very powerful way of breaking down proportions of values. So here we've a pie chart, and we're going to set out here, again, we're bringing in the library. So we've got to, now we've already imported Matplotlib, so pie.plot as plt. So in fact, we could run this code again, and we could neutralize, we could leave out import. We could neutralize that. It still will run perfectly. There'll be no issues because we've already imported that in. But just for completeness, we'll leave it live here. And then we've labels S1, S2, S3, S1, S2, S3. And then the magnitudes 56, 66, and 24. Right, 56, 66, 24. So if we sum those values here, let's just Control Z and come down below into a code cell, Control V. So I'll Control V, and sum up 56. So I take 56, take the 56 plus 66 plus 24, and we run that, we get 146. And if we take, in fact, if we take 56 and divide it by 146, we get 38, 35, 38, 36. So we're rounding up. If we take 66 and divide it by 146, we get 42, 25, 42, 20.5. So 45.21 corresponds. And again, we take the 24 and run that again, you can see how we're producing the 16%. Okay, so that's a nice automation within the code in terms of generating, once we feed in the data, the number of observations or the number of counts on a particular categorization. Here along the lines of S1, S2, S3, the rest is performed automatically for the graph. Okay. The plt pi generates a graph, so various parameters can be adjusted to customize the appearance. Start angle rotates the start of the pie chart. Explode offsets a slice of the center. And auto PCT labels the slices with their numerical values. So if we want to go 3 decimal places or 4 decimal places, which sometimes might be desirable, you can see here we've gone out to 4 decimal places. And here we got that sense of exploding, right? So explode, let's put in 0.4 or let's put in 0.7 and accentuate the graph. So that's possibly too much, doesn't make sense. So the 0.1 or 0.2 makes sense. And let's do another 0.1 or 0.3. Okay, so again, you can construct this graph in different ways to give different accentuations, different levels of emphasis. Okay, a very nice way of filling your graph is put a green background, right? So line chart, again, it's a line chart, but filled regions using Matplotlib. And this script demonstrates how to create a line chart with regions filled below the line using Matplotlib library in Python. Additionally, it shows the use of alpha, the alpha parameter for transparency. Okay, so we have to generate the values as before. So this time the values are going to center around 200, but we'll have a normal distribution of a mean of 0 and a standard deviation of 1. So the mean value here would be 200, but then would have a standard deviation of 1 and a normal distribution. And then we count the values 1, 2, 3, 4, 5, 6, 7, all the way up to 100. And then we plot the data and fill the regions below the line. Regions where the data exceeds 195 are filled with a green color using fill between. So to plot x's from 195. Okay, so let's see if we can change a few of our parameters. Let's change it to blue or to red. Okay, we get a red, nice background. Let's lower the transparency to 0.1. So it has the effect of lightening the color. And let's say 195. Okay, let's go with 50. 50. Let's go with back to 195. So we've pushed down to 60, as you can see. Let's go 195. 195. Okay. Let's go 180. Okay, so you can see we can control the dimensions of the data. Sometimes you want to see just the pattern here, so you need to emphasize a little bit, provide more stretch in terms of the jaggedness of the graph. And in that instance, then you'd go up to the value 195 would make sense. Okay, so you can see we're starting here at 195.